Good day, doctor. My name is Sarvina Suryamuthi, and today our Group 3A will be comparing two octahedral coordination complexes, namely hexa-aqua-titanium 3 ion TiH2O6 3+, and molybdenum hexacarbonyl MoCO6. Although both complexes have the same octahedral geometry and coordination number of 6, they differ significantly in terms of their metal centers and ligand properties. These differences will later influence their crystal field splitting, magnetic behavior, and metal ligand bonding. Let's first look at the basic characteristics of each complex. For hexa-aqua-titanium 3 ion, the central metal ion is titanium in the positive 3 oxidation state. The six surrounding ligands are water molecules, which are known as aqua ligands. Water is a neutral ligand and is generally classified as a weak field ligand in the spectrochemical series. On the other hand, molybdenum hexacarbonyl contains molybdenum as the central metal atom with an oxidation state of 0. The six ligands are carbon monoxide molecules, also known as carbonyl ligands. Carbon monoxide is a strong field ligand and is well known for its strong metal ligand bonding interactions, particularly its ability to accept electron density from the metal through pi back bonding. Next, we'll determine the oxidation state and d-electron configuration of metal centers. For hexa-aqua titanium 3 ion, all six water ligands are neutral, so the overall charge of plus 3 must come entirely from the titanium ion. Therefore, the oxidation state of titanium is plus 3. Titanium has the electronic configuration of argon 3d2 4s2, and after losing 3 electrons, Ti3 plus has a d1 configuration. For molybdenum hexacarbonyl, carbon monoxide is also a neutral ligand and the complex is overall neutral. Therefore, the oxidation state of molybdenum is 0. Since neutral molybdenum has the configuration of krypton 4d5 5s1, it contains 6 d electrons and is classified as a d6 system. When these d electrons are placed in an octahedral crystal field, the electron arrangements become T2G1 Eg0 for hexa-aqua-titanium 3 ion and T2G6 Eg0 for molybdenum hexacarbonyl. These differences in ligand strength and electronic configuration provide the foundation for understanding the crystal field splitting patterns and molecular orbital interactions, which will be discussed in the next sections.
Good day to doctor and friends. My name is Leong Libing. I will explain the crystal field theory analysis of these two octahedral complexes. First, let us consider hexa-aqua titanium 3 ion. Based on spectrochemical series, aqua is a weak field ligand, so it will produce a relatively small octahedral crystal field splitting energy compared to strong field ligand. Titanium 3 plus has D1 electronic configuration. The electron will occupy lower energy T2G orbital, so high spin or low spin terms are not really applicable in this case. Because there is one unpaired electron, the complex is paramagnetic. Since the crystal field splitting energy is small, the energy gap between T2G and EG orbital is also small. Therefore, only a small amount of energy is required to promote electron from T2G to EG orbital. Consequently, the complex absorbs light of longer wavelength. The color of complex arises from DD electronic transitions. When visible light is absorbed, the electron is excited from T2G to EG orbital. The complementary color of absorbed light is observed, which in this case is purple. Next, let us consider hexacarbonyl molybdenum 0. Carbonyl is a very strong field ligand, which contributes to large splitting energy. Since the splitting energy greater than pairing energy, the electron will pair up in lower T2G orbital before occupying EG orbital, forming a low spin D6 electronic configuration. Since all electrons are paired, the complex is dimagnetic. Because crystal field splitting energy is large, the energy gap between T2G and EG orbital is also large. Therefore, more energy is required to promote electron from T2G to EG orbital. As a result, the complex absorbs light of shorter wavelength. However, this large splitting energy shifts DD transition into UV region, resulting in little or no absorptions in visible region. Therefore, it appears colorless. That's all from me. Thank you.
Next, I will talk about part C, which is the molecular orbital theory analysis of hexa-aqua titanium 3 ion. So for this metal complex, the titanium 3 is a transition metal with a 3 positive charge, where its valence electron configuration is a D1 system with an octahedral geometry. Next, I will talk about the metal orbital symmetries involved. Uh, the metal orbital symmetries are broken down. For sigma bonding, the metal uses its 4s orbital, labeled here as A1G symmetry, and its 4p orbitals with a T1U symmetry to overlap strongly with the incoming water ligands. At the picture beside on the left hand side, the molecular orbital diagram can show that the atomic orbital mix to form the high energy T1U and A1U antibonding tracks. Next, the D3 orbitals on the left side of the graph, they will split into two groups. The axial DX and DX2 Y2 orbitals with EG symmetry point directly at the ligands to form the antibonding EG levels at the top of the middle column. So as the highlighted of the bottom right, the DXY, DYZ, and DXZ orbitals have T2G symmetry. Because they point between the axes, they have zero initial sigma overlap, which leaves them sitting as the unshifted non-bonding T2G track containing one one single D1 electron. So next we look at the ligand group orbitals. So this contributes to the core of the sigma skeleton. Looking at the central column, the 6 lone pairs from the water oxygen combines to form 6 symmetry adapted ligand group orbitals under the A1G plus T1UN plus EG sets. Looking at the graph on the left, there are ligand orbitals that are placed significantly lower in energy than the titanium 3D orbitals. This position is due to the high electronegativity of oxygen, which holds its electrons very tightly. So when this makes the bottom of the baseline electron arrangement, the 12 ligand electrons completely fill this low energy. The ligand dominates the bonding molecular orbital, which are labeled here as A1G, T1U, and also EG. This satisfies the 6 sigma bonds of the octahedral core, leaving the single metal derived as D1 electron to sit alone in the non-bonding T2G level. That's up as our baseline for the non-bonding T2G level, setting up our baseline for the delta oct gap before we turn on any secondary pi effects. Next, we will look at the ligand characterizations of to learn more about the secondary pi interaction with our water ligands. So H2O acts as a primary sigma donor through one oxygen lone pair. So however, it possesses a second field p orbital lone pair on the oxygen atom perpendicular to the sigma bond, acting as a weak pi donor. This field ligand pi orbitals combine to form LGOs with T2G symmetry because they belong to an electronegative atom. These field ligand pi orbitals sit lower in energy than metal d orbitals. Now let's look at the effects on T2G and the delta octahedral. The field ligand T2G orbitals mix with the metal T2G orbitals, driving a repulsive bonding or antibonding split. The metal dominated as T2G set is pushed outward in an energy to become antibonding T2G. The gap between the T2G and EG narrows, leading to a smaller delta octahedral, which gives a weak field complex. Next, we will look at the ligand characterizations of to learn more about the secondary pi interaction with our water ligands. So H2O acts as a primary. So for the next is molecular orbital theory analysis meta complex is the molybdenum hexacarbonyl. So for the first metal center basics, the molybdenum is a neutral zero oxidation state, giving a much denser D6 valence electron configuration. The molybdenum is a second row 4D transition metals, and it follows the same symmetry as the titanium, which is a octahedral geometry. Next is the metal orbitals symmetries involved. It uses its 5s orbital for A1G and 5p orbitals for the T1U to build the baseline of sigma tracks. The tracks on the molecular orbital diagram on the left is that the 4D orbitals, which is EG, points directly along the axis to form high energy antibonding EG level. Just like before, for the titanium, it forms 4D XY, 4D YZ, and 4D XZ orbitals that points between the axes and experience a zero direct sigma overlap. This leaves with a non-bonding T2G in the center of the diagram, where 6 valence electrons are waiting to be arranged in the orbitals. So next, we will look at the ligand group orbitals. For each of the 6 CO ligands possesses a lone pair on the carbon atom, pointing directly along the Cartesian axis towards the molybdenum center. The carbon lone pairs are highly stable, where the 6 sigma sit much lower in the energy than the metals or the atomic orbital. So for the baseline electron arrangement, when they mix with the metals 5s, 5p, and the EG4D orbitals, they create a 6 strongly bonding and molecular orbitals that hold the 12 electron donated by the ligands. So because these are antibonding orbitals of the isolated CO molecule, the pi ligand group orbitals have sit higher in energy than the metals of the 4D orbitals. So finally, the ligand characterization of molybdenum. The carbon monoxide is a powerful pi acceptor ligand. So beyond its initial sigma donor, the lone pair, it possesses empty low-like antibonding pi orbitals. The empty pi orbitals on the sigma ligands match the T2G symmetry of the metal. Because they are antibonding molecular orbitals of the ligands itself, they lie higher in energy than the metal 4D orbitals. So looking at the image beside on the left, the diagram shows that the filled metal T2G orbitals are perfectly aligned to the overlap of the empty ligand pi orbitals, allowing the metal to dump its excess electron density back onto the ligands through the strong pi back bonding. The effect of T2G and the delta octahedral, the filled metal T2G orbitals overlap with these empty ligands pi orbitals, donating electron density back to the ligand via pi back bonding. This bonding interaction strongly stabilizes the metal center T2G set, shifting its downward in energy. This results in the lower of energy of the T2G set, significantly widens the gap between the T2G and the anti-bonding EG level, creating a massive delta octahedral gap, which becomes a strong field complex. Due to the large delta octahedral, the pairing energy is easily overcome. So finally, the ligand characterization of molybdenum. The carbon monoxide is a powerful pi acceptor ligand. So beyond its initial sigma donor, the lone pair, it possesses empty low-like antibonding pi orbitals. The empty pi orbitals on the
And now for the further comparison between hexa-aquatitanium 3 ion and molybdenum hexacarbonyl based on the CFT theory and molecular orbital theory. Starting with ligand strength, water is a weak field ligand, whereas carbon monoxide is a strong field ligand. Therefore, hexa-aquatitanium 3 ion has a smaller delta octahedral, while molybdenum hexacarbonyl has a larger delta octahedral. This leads to a different electron arrangement. For the electronic configuration for hexa-aquatitanium 3 ion, It has one electron in the T2G orbitals and none in the EG orbitals, making it a high spin complex. In contrast, molybdenum hexacarbonyl has all 6 d electrons occupying the T2G orbitals, making it a low spin complex. In terms of magnetic behavior, hexaquaternum 3 ion contains one unpaired electron, making it a paramagnetic, while molybdenum hexacarbonyl has no unpaired electron and is diamagnetic. The two complexes also differ in color and bonding. Hexaquaternum 3 ion appears violet or purple and mainly exhibits sigma donation, whereas molybdenum hexacarbonyl is colorless to pale yellow and shows both sigma donation and pi back bonding, which result in stronger metal ligand and greater stability. The two complexes are also differ in color and bonding. Hexaquaternum 3 appears violet or purple and mainly exhibits sigma donation, whereas molybdenum hexacarbonyl is colorless to pale yellow and show both sigma donation and pi back bonding, which results in stronger metal ligand bonds and greater stability. And now for the further comparison between hexaquaternum 3 ion and molybdenum hexacarbonyl based on the CFT theory and molecular orbital theory. Starting with ligand strength, water is a weak field ligand, whereas carbon monoxide is a strong field ligand. Therefore, hexaquaternum 3 ion has a smaller delta. Based on this comparison, molybdenum hexacarbonyl has the larger delta octahedral because CO is a strong field pi acceptor ligand. The strong ligand field causes greater splitting of the orbitals. As a result, molybdenum hexacarbonyl is a low spin complex with all the d electrons paired in the lower energy T2G orbitals. In contrast, hexaquaternum 3 ion has only one d electron, so it remains unpaired, making the complex paramagnetic. Another important difference is the bonding. CFT explains orbital splitting, spin state, and magnetic behavior, but it cannot explain the nature of the metal ligand bond. Molecular orbital theory provides a deeper explanation by describing orbital overlap. In molybdenum hexacarbonyl, CO not only donates electron density to the metal through a bonding, but also accepts electron density back through pi back bonding. This additional interaction strengthens the metal ligand bond and increases the stability of the complex. Therefore, CFT is useful for predicting electronic properties, while molecular orbital theory gives more complete explanation of bonding, especially in the complex containing pi acceptor ligands such as CO. Based on this comparison, molybdenum hexacarbonyl has the larger delta octahedral because CO is a strong field pi acceptor ligand. The strong ligand field causes greater splitting of the orbitals. As a result, molybdenum hexacarbonyl.
In conclusion, which complex has the stronger ligand field? First, for the molybdenum hexacarbonyl has a much stronger ligand field. Hexaquaternum 3 ion, aqua H2O, is generally classified as a weak field to intermediate ligand. Additionally, titanium ion is a 3D transition metal. Next, for the molybdenum hexacarbonyl, carbonyl is a classified strong field ligand near the very top of the spectrochemical series. Furthermore, molybdenum is a 4D transition metal. Metals in 4D and 5D series has much larger orbital overlap with ligands, which inherently increases the crystal field splitting energy compared to 3D metals. Which complex is high spin or low spin? For the hexaquaternum 3 ion is neither. Titanium is in a +3 oxidation state here. Naturally, titanium is Ar4s2 3d2, so titanium ion has a d1 electron configuration. Next, for the molybdenum hexacarbonyl, this is a low spin. Molybdenum is a 0 oxidation state here. Naturally, molybdenum is a 4d5 5s1 metals, which give it 6 valence electron, d6 configuration. Because carbonyl is a powerful strong field ligand and molybdenum is a 4D metal, the splitting energy is massive. Here, all 6 electrons are forced to pair up completely in the lower energy T2G orbitals. Next, which complex is paragmatic or diametric? Hexaquaternum 3 ion is paragmatic. It contains exactly 1 ampere electron in its d orbitals. For the molybdenum hexacarbonyl, is diametric because it is very low spin d6 complex. All 6 electrons are completely paired up in the 3 T2G orbitals. Here are 0 ampere electrons. Other than that, how does MOT explain the results better than CFT alone? The CFT flaws. CFT treats ligands purely as point charge. H2O has a partial negative charge on its oxygen atom due to a dipole, while carbonyl is a natural molecule with a very small dipole moment. Purely electrostatically, CFT struggles to explain why natural carbonyl splits the d orbital drastically further apart than H2O does. The CFT flaw. CFT views ligands strictly as electrostatic point charge. Under this logic, the polar dipole of H2O should cause a larger d orbital splitting than the natural carbonyl. In reality, the opposite happens. Carbonyl, pi acceptor, forms a strong sigma bond, but more importantly, its empty, low-lying pi orbitals accept back-donated electron from the metals T2G orbitals. This interaction stabilizes lowers the energy of the T2G level, massively widening the gap. H2O, a sigma donor, acts primarily as a standard electron pair donor because it lacks empty, low-energy pi orbitals for back bonding. There is no extra stabilization to lower the T2G energy, keeping relatively small. The MOT resolution. MOT looks at covalent orbital overlapping and symmetrically, classifying ligands by how they share electrons. Next, for the Q&A. For the first question, how did you determine the oxidation state and d electron count of the metal in each complex? First, for the hexaquaternium 3 ion, water is natural, so it is zero. Titanium has 3 charge, so it is a D1 system, which means 1 valence electron. Next, for the molybdenum hexacarbonyl, carbonyl is natural, so it is 0. Molybdenum has a 0 charge, and it is D6 system, which means 6 electron valence. For the next question, based on crystal field theory, how are the d electron arranged in each complex? In an heptahedral field, d orbitals split into a lower level T2G and a higher level EG. First, for the hexaquaternium 3 ion, the single electron sits alone in the lower level TG1 and EG0. Next, for the molybdenum hexacarbonyl, because the energy gap is huge, all 6 electrons are forced to pair up in the lower level T2G6 and EG0. Next, for the which complex has the larger, and how does this affect the color, spin, state, and magnetic behavior? Molybdenum hexacarbonyl has a larger energy gap because carbonyl is a strong field ligand and molybdenum is a larger for the metal. For the color, hexaquaternium 3 plus has a small gap, absorbs visible light, and looks purple. For the molybdenum hexacarbonyl has a massive gas gap, absorbs invisible UV light, and is colorless. For the spin state, hexaquaternium ion has too few electrons to choose, but its high spin unpaired. For the molybdenum hexacarbonyl, it is strictly low spin, it is forced pairing. Next, for the magnetism, for the hexaquaternium ion, it is paragmatic and has 1 ampere electron. However, for the molybdenum hexacarbonyl, is diamagnetic, all electrons are paired. Next, for the question 4, how does molecular orbital theory explain the difference between the two complexes better than CFT alone? The CFT flaws, CFT treats ligand as a simple negative point charge. It cannot explain why naturally carbonyl creates much stronger field than fully charged negative ion. The MOT solution, MOT accounts for covalent orbital overlap. It explains that carbonyl uses pi back bonding. The metal shares electrons back into the empty orbitals of carbonyl. This lowers the energy of the bottom orbitals, which dramatically widens the gap. Water cannot do this. Next, for the 5th question, based on your CFT and MOT analysis, which of the two assigned complexes has the stronger ligand field, and how does this explain the differences in spin state, magnetic behavior, and the bonding strength? Why? Because it is used two-way strict bonding system. Carbonyl gives electron to the metals, which means sigma donation, and the metal gives electrons back, pi back bonding. The result, this double bonding interaction drastically widens and makes the chemical bonds incredibly strong, forces all electrons to pair up, low spin or diamagnetic, and shift its light absorption out of the visible spectrum, colorless.